Okay, thanks, Hannah. And, good to be at this meeting with everybody here today. It's obviously attracted a lot of interest. There's a lot of people here. So, and I've been finding it really interesting. Today, the talk that Chris and I have prepared is called Operationalizing Techniques for Scaling Up Coral Restoration. And it's a technique that uses coral spawn slicks. Now, this is something that has been very exciting to me personally since, back in the early 1980s, I was working at James Cook University on the Great Barrier Reef and was part of a team that discovered mass spawning of corals there. And it was pretty early on in that time that when we saw coral spawn slicks, we started imagining what could be done with these billions of coral larvae and the potential for using them to help restore reefs. Unfortunately, not many other people shared that vision for a long time. And I guess the perceived need to be able to restore reefs was not really seen as being very urgent. It was thought, we'll let reefs take care of themselves. Well, it's clear now that reefs are going to need some help from us, perhaps a lot of help. And so the interest in using coral spawn slicks came alive again. And so we started some work to try to test out various methods that we thought needed to be proven if we were ever going to be able to do coral restoration at a large enough scale to be, large enough scale to be ecologically meaningful. So that's our story today. And it's not just Chris and I, of course, who have done this. We're part of a large and diverse team. Chris, if you could bring up the next slide. So a couple of years ago, we started doing this work. It was funded by the Queensland government and CRRRW. And also we had some partners in business in the form of Van Oord, which is a large marine engineering company. So on the CSIRO side, we have a number of people involved in the field work, but also oceanographic modelers who helped us work out the best places to try to find slicks. We had people who did remote sensing who could help us try to locate the slicks. Also, people from other parts of CSIRO who were experts in fluid dynamics and a range of other support that we had to try to bring off this work. From the side of Van Oord, of course, we've done the research throughout the decades in CSIRO, but Van Oord, although it's an engineering business, have also done some research of their own, both in terms of relocating corals from areas that have had to be dredged, also setting up mobile larval culture laboratories, and also in this work with us. So they're trying to minimize and offset the impacts of the kind of engineering works that they do. So they're experts in pumping large volumes of seawater, transporting large volumes of seawater, and understanding the mechanics, the engineering, the physics, as well as the ecology. So they were kind of an ideal partner when we were looking for someone that we could team up with to try and investigate making this possible on a really large scale. And we had a lot of support from other industry too. People helped us access pumps. We got support from a tug company whose vessel we used for this work, and also from the University of Queensland. So it's been a very exciting time. We see a lot of potential for this in the future, and we're very excited to be able to be part of this today and to talk with you guys about the potential that you might see in it and some other, any other ideas that you have about how it might be.
And some work also into capturing coral spawn, and that's been done in the Caribbean as is photographed here, as well as other parts of the world. especially in Japan and the Philippines, for example, and some work in Palau and now some work in Australia too. But a recent-ish analysis also provided that there's some historical problems with these approaches, that production is quite low in terms of how many colonies are produced, that the scale at which these work is done is often quite small, and it's been a lot, has been driven a lot by experimental work, and the median costs have been historically high as well. Now these are medians, and there are outliers either way as well. So there are examples of really low cost techniques as well, and really large scale studies as well. And these are coming out more and more in the literature and from practitioners. And there's, you know, some success story examples as well, and I've just highlighted two here. The one on the left of the screen is from Belize, and the particular example here is using 40 coral fragments, and you can see that from 2010 to 2020, there was a massive change in coral cover over that reef patch. Some other work from the Philippines by Dexter de la Cruz and Peter Harrison is shown on the right, and that's actually where they used coral spawn that was harnessed and then put back onto the reef with nets. And those colonies, I think it's 4 or 5 years later now, they have been spawning and reproducing. Some of our previous work, early work with Van Ord, it kind of began in Ningaloo Reef, which is in northwestern Australia. And that was conducted in the reef guard facility that Van Ord developed. And that was, again, collecting gametes and settling those onto thousands of plugs, and then essentially developing those out in a nursery in lagoonal areas. And then they can then be grown out at restoration sites and put out into the water. And as you can see, just by the time series here, that these corals they grow pretty fast, and they would be reproductive now. But still, we still have this problem, and that is the question of how can we scale up the 2 to 3 orders of magnitude to produce tens or hundreds of thousands of corals needed for large-scale restoration. So I'll just provide an outline of our approach for this work that we've been conducting. And the first start was modelling and conceptualisation of our technique. The second is to do some first empirical trials to test some feasibilities of this technique. And we had questions and assumptions in our modelling and conceptualisation that we needed to test before we were happy to move forward, which is the third step. That was to evaluate the empirical field trials, and then to move this forward and think about, well, what needs improvement and how are we going to then further this approach. So the first part of the work is the conceptualization of slick harvesting, transporting, and release. As I mentioned, this was conducted using a demographic model, and to do that, we used the best data that we could find in the literature, and if data wasn't available from the literature or our own unpublished works, we had to make some assumptions. But it follows the coral life history. On the Great Barrier Reef, we have a really good idea of when corals are going to spawn and the amount of eggs that corals release. So we could model that, and then we use the approach of harnessing those coral spawn slicks in oil booms to concentrate them and hold them in position, while the mothership could come up to that slick and then suck it off the surface. And that mothership is essentially where the culture would occur. So we assume that for quite a large hopper dredge, we could at least collect about 2 billion live coral embryos. So that's following fertilization. And we made an assumption that there'd be about 25% mortality from the pumping itself. We assumed about 5 days for the embryos to become competent larvae, and suffering a 75% mortality loss over that time. So following those 5 days, the model shows about 500 million competent larvae that could then be released back onto a reef, which would give us 8 million settled corals, which equates to about 140,000 mature coral colonies 4 years later. But as I said earlier, there were quite a few assumptions with this and few unknowns that we need to test. And so for what the rest of the work that I'm going to present now, that concentrates on this part of the life phase, the first part, up to settlement and before release. So the second step of our trial of this presentation is how we evaluate empirical feasibility. So we had 5 major questions which we wanted to test and address, and that is, can we use oil booms to contain and concentrate slicks? The second part of it was, well, can we find live embryos in slicks at greater than 230 per litre, which is the only published information that we could find at the time. Will the larvae survive pumping once we find them? And will there be differences in larval survival between plastic and steel tanks? So the literature would suggest that there is, but that has never really been tested at scale. And if we were to move to commercial vessels that had steel hopper dredges, we would need to know whether the larval culturing could occur in that. And lastly, could we actually rear those larvae until competency on a vessel on this moving kind of aquaculture facility? Just our fieldwork pipeline was firstly to select our area. And so we're fortunate to have access to really long-term monitoring throughout the Great Barrier Reef. And at that time, the Southern Great Barrier Reef had the highest coral cover in general for the Great Barrier Reef itself. So that's where we aim to work, around Heron Island and Wistari Reefs in this area of the Great Barrier Reef, which is more or less a very southern end. We needed to determine the timing of the coral spawning. And as I suggested earlier, we have quite a good understanding of when that happens on the Great Barrier Reef. Then we modelled the spawn slick locations. And of course, we had to prepare our team and equipment, which some parts were done in Australia and some parts were done in the Netherlands, especially related to the pumping. And we're really fortunate at CSIRO to have some great modelers. And so we were able to put up some predictive models of where we thought these spawn slicks would be based on those 2 different reefs, coming off those 2 different reefs. So how did we go? Well, the first is just an image here of using those oil booms to contain the slicks, and actually locating and containing the slicks wasn't a major hindrance, and we were able to do that really, really well. And we had great weather, so it was really good working conditions. But once we had that slick contained, we did have some issues manoeuvring, and that's related to the amount of drag that the boom created for the smaller vessel that was dragging it around. And there's some ways we could improve on that in the future. The second aspect was, well, would we find and could we concentrate coral embryos greater than 230 gametes per litre? That was not a problem at all. And the kind of concentrations we found were way well above our expectations. As you can see, the mean that we found was 170,000 live embryos per litre. So that doesn't seem to be an issue. And even following pumping, we still had really high concentrations of embryos. So what I'm showing here in this table is where we actually collected some of the slick and poured it straight through the pumps, and what we have afterwards. So we have really high concentrations. Where we had further troubles though, is where we tried to pump the slicks directly off the surface of the water. And you can see here that actually we have quite a lot lower concentrations of those live embryos in the tanks when we try to pump directly from the water surface. So that's something that we're looking to improve upon. And testing between the 2 different pumps. So we used a diaphragm pump, which is an air-driven pump. And we also use this other kind of pump, which is called a hydrostat pump, which is an electric-driven pump. And when we look at the survival following pumping, well, survival was extremely high, and it's actually greater than 100% generally. And that's because we had some fragmentation of those embryos when we pumped them. But those embryos, they fragmented, but they still survived and went through development. We also tried this when the larvae were competent as well. They're very low replication because we only had a few of these tanks to work with. But again, we feel that this data is kind of showing to us that pumping the larvae is not really a problem with these two types of pumps. And they were really large pumps, so there's not too much stress on those particles. Just a quick kind of time lapse of how the operation worked. And you can see that's the mothership that we're looking at. And then the small boat coming in and releasing those concentrated slicks next to it to be collected from. And as you can see, it's quite a large setup. So just going into a bit of detail about that setup. Oh, sorry, there's a bit of background noise. So just going into a little bit of detail about that. Sorry, could everybody please mute? I'm getting a lot of background noise, if that's possible. That's great, thanks. So just going into that setup, we just use a pretty typical aquaculture setup, which is a high throughput approach for invertebrate larvae. So what we had was constant flow through water, and that came through two-stage filters of about 50 micron and then 5 microns. And then before they went into the tanks, it also went through a large UV filter. The flow was such that each tank turned around 2 times per day at a minimum. And the tanks that we used were rainwater tanks. So they were about 4,500 litres in size. And it was set up with a bubble curtain and a constant flow of water coming in and then coming out and just dribbling out over the side. And as you saw in that video, this is kind of what it looked like set up. So we just had some replication and things like that. So we could test different pumping and different survival in the 2 different tanks. So when we look at the survival in the 2 different tanks, we have those 2 questions of are there differences in survival between the tank types and then between the pump types? And there wasn't. So overall, we had about 14% survival, which is really high at this kind of scale. It's amongst the highest or recorded in the literature. And some of our initial stocking densities were quite high. And so we in the future, this is something that we want to test to really optimize, like what is the best initial starting density. And you can just see from this small microscope image on the right-hand side that we had a full diversity of gametes of different kind of coral types in our cultures. And our final question was, well, could we culture these larvae on vessels till settlement competency? And yes, we can. We had extremely high settlement rates. You know, on the top sides of the tiles, the average is 7 individuals per centimetre square. And that's double that on the undersides of the tiles. On average is 15 settlers, sorry, per 15 centimetre square. And you can see some differences here with a diaphragm pump in the steel tanks. And maybe that was a bit related to the slightly warmer temperatures in those. So if we evaluate the effectiveness of our trial, well, can we use our oil booms to concentrate the slicks? Well, yes, we can, but we do have some issues with manoeuvring and small losses of the slicks coming under the skirt of that boom when we try to manoeuvre too fast. Can we concentrate coral embryos greater than 230 per litre? Well, yes, that's definitely not a problem. But there are some issues with transferring from the surface of the water directly into the containers. So that's something we're looking to improve. Larval survival was really high following pumping. We're really happy with that, as well as survival in the different kind of tanks, and no worries about rearing these until competency. So where are we now? What are our next kind of steps to mass production and transfer? And the first major thing thing is to work on this side of the diagram, that we need to improve our collection and transfer techniques. And we're going to be doing this using some passive boom systems and some active surface skimmer approaches as well. We're really happy with the culturing on the vessel in these tanks, but we're also now going to trial with our partners to mass culture in situ. So that's using reef pools, and we're going to do some manipulations to larvae as well during that to see if we can enhance their survival or growth. And then the deployment requires quite a fair amount of development and testing. And there's three major things we're going to be looking at, and that's surface to benthos releases, robotically assisted releases, and indirect releases, so using devices as well, like will go onto the reef. And a lot of that work is on the Great Barrier Reef is going to happen from now until the next 4 years as part of the Reef Restoration and Adaptation program that's occurring. And our two major partners for the work along the Great Barrier Reef are Southern Cross University and Queensland University of Technology. So I'd just like to finish up there, and thank you all very much for attending and for having us. And I'll just open up for questions and discussion.